Welcome to The Explainer. Today we are diving into one of the most clever inventions in engine technology, the turbocharger. I mean, just think about it. It's a device that takes something an engine just throws away and literally spins it into raw power. It's pretty incredible.
All right, let's jump right in. To really get why the turbo is such a game changer, we've got to first talk about a basic problem, a challenge, really, that every single internal combustion engine has to deal with.
So this was the million-dollar question for engineers for decades. How can you make a small engine punch way above its weight? You know, how do you get that big engine performance without the big engine size, the extra weight, and of course, the terrible fuel economy? Well, the answer turned out to be all about recycling energy that was already being wasted.
You know, when you really boil it down, an engine is basically just a giant fancy air pump. Seriously, it pulls air in, mixes it with some fuel, creates a little controlled explosion, and then pushes all the exhaust out the back. And the golden rule here is super simple. The more air you can stuff into those cylinders, the more fuel you can burn, and you guessed it, the more power you're going to make.
Now this is your standard engine. It's called naturally aspirated, which is a fancy way of saying it just breathes naturally. It sucks in the air around it at whatever the normal atmospheric pressure is with no extra help. It's simple, it's reliable, but there's a definite ceiling to how much power it can make.
So in the old days, if you wanted more power, what did you do? Well, you just made the engine bigger. You added more cylinders, you increased the displacement. But that sets off a chain reaction of problems, right? The engine gets way heavier, it takes up a lot more space, and your fuel efficiency, well, that just goes right out the window.
But here's the brilliant idea. What if you didn't need a bigger engine? What if you could just force feed more air into the same engine you already have? And what if you could do it using a power source that the engine is already producing and just throwing away? Well, that's exactly where the turbocharger makes its grand entrance.
The whole concept is actually beautifully simple. Just picture two tiny fan wheels connected by a single shaft. You've got the hot side, or the turbine. It lives in the exhaust stream and gets blasted by all the hot gas flying out of the engine. That's pure waste energy. This makes it spin like crazy. And since it's connected to the other fan, the cold side, or compressor, that one starts spinning too. Its job is to suck in fresh air, compress it, and force it back into the engine. And when I say it spins like crazy, I am not kidding. This all happens at just mind-boggling speeds. That little shaft can spin at over 250,000 revolutions per minute. Just think about that, 250,000 RPM. It is an absolute marvel of engineering, a tiny, high-speed, super hot ballet happening under the hood, all designed to turn waste into boost. So this is the real magic trick. The size of the cylinder itself, that's not changing, but the air inside it is getting way more crowded. By compressing the air, you are literally stuffing more oxygen molecules into the exact same physical space. And more oxygen means you can burn more fuel, which gives you a much, much bigger bang from each combustion event.
Okay, but a turbo is so powerful, you can't just bolt it on and call it a day. All that compression creates some, let's call them side effects. So it needs a supporting cast, a couple of absolutely critical systems to help manage everything and keep the engine safe.
And to understand this next bit, we just need a quick trip back to basic physics. Don't worry, it's something you've probably felt yourself if you've ever used a hand pump on a bicycle tire.
Remember how that pump gets hot? Well, that's because when you squeeze air molecules together, they create friction, and that creates a lot of heat. So the air coming out of that turbo isn't just pressurized, it's also really, really hot. And here's the problem. Hot air is less dense, which kind of defeats the whole purpose of what we're trying to do.
And that's where the intercooler comes in. It's basically a little radiator, but for the intake air. The hot, pressurized air from the turbo flows through the intercooler, which cools it way down. This cooler air is much denser, and that's exactly what the engine wants. It lets it pack in even more oxygen and make more power, but safely.
So what stops the turbo from just spinning faster and faster until it creates way too much pressure and blows up the engine? That's the job of the wastegate. Think of it like a bypass valve or a floodgate. When the pressure gets too high, the wastegate opens up and lets some of that exhaust gas go around the turbine instead of through it. It's a pressure regulator, and it's what keeps the turbo from destroying itself and the engine.
Now, we often think about turbos in the context of high-performance cars, but they are arguably even more essential in a completely different field, one where the air itself is the biggest challenge: aviation.
As an airplane climbs, a normal engine basically starts running out of breath. The air gets thinner and thinner. For every 1,000 feet you go up, a naturally aspirated engine loses about 3% of its horsepower.
And that is a huge problem if you're trying to, say, cross a mountain range.
And this leads to two different jobs a turbo can have on a plane. On one hand, you have a turbo-normalized system. This thing is playing defense. Its only job is to compensate for the thinning air to basically trick the engine into thinking it's still down at sea level. On the other hand, you've got a ground-boosted system. This one plays offense. It's designed to force-feed the engine more air than it would even get at sea level, increasing its power right from the start.
So you can see how the mission completely changes the design. A car turbo is all about instant response for zipping through traffic, which leads to really complex tech to reduce that turbo lag. But for an airplane, the #1 goal is sustained, reliable power in thin, dangerous air. A simple, robust wastegate system is way more important than anything else.
So, we've seen the magic of how they work. But like any piece of technology, it's not all upside. There are some very real-world trade-offs we have to talk about.
The benefits are just undeniable. You get a massive power boost. We're talking 30, even 40% more from a smaller, more fuel-efficient engine. It's kind of like getting the power of a V8 with the fuel economy of a V6. And of course, it's a miracle worker at high altitudes.
But that performance comes at a price. Turbo lag is that classic delay you sometimes feel while waiting for the whole system to spin up. And more fundamentally, you're adding a really complex, high-speed, high-heat component to your engine. That means more plumbing, more parts that can fail, and a lot more thermal stress on everything. You know, the turbocharger is a masterpiece of mechanical problem-solving. It is just a brilliant way to make combustion engines more powerful by recycling their own waste. But as we start to enter an electric future where instant torque from a motor is just the norm, the turbo's days really seem to be numbered. It might just stand as the ultimate, most ingenious refinement of the internal combustion engine, a fascinating final chapter in a century-long story of power.